Have you ever really stopped to think about what's happening inside your computer? I mean, how does this box of metal and silicon actually, well, think? In that tiny fraction of a second between you clicking a button and something happening on screen, there's this incredible, super fast drama playing out. And today, we're going to follow that story.
I mean, seriously, it feels like magic, doesn't it? It's like there's a little ghost in the machine that just instantly understands what you want to do. Well, I've always wanted to find that ghost. So today, that's exactly what we're doing. We're going to follow a single command on its journey from your brain to the computers and see how it all really works.
So, here's our roadmap. First, we'll tackle the big picture, the difference between a computer's blueprint and how it's actually built. Then, we'll meet the key players inside the box, learn their secret language, and watch the simple three-step dance that powers, well, everything. You're gonna want to stick around, because the scale at which this all happens is just, well, it's mind-blowing.
All right, first things first. To really get how a computer works, you have to separate the idea of the computer from the actual physical thing. In the tech world, we call this the difference between architecture and organization. Okay, think of it like this. The architecture is the blueprint for a house. It tells you what the house does, where the rooms are, what the rules of the house are. Now, if you're a programmer, you're like someone living in the house. You just need to know the rules to get things done. The organization, on the other hand, is how the house was built. The specific type of wiring in the walls, the brand of pipes they used. Two houses can have the exact same architecture, the same blueprint, but be built or organized completely differently. It's the exact same for computers. So we've got the blueprint. Now let's meet the crew that actually does the work. Turns out, pretty much every digital computer you've ever laid hands on relies on the same three core parts to function. First up, we've got the star of the show, the CPU, the central processing unit. This is the brain. It does all the thinking, all the heavy lifting. And inside the brain is a special part called the ALU, the arithmetic logic unit, which is basically the computer's super-fast calculator. Next, there's RAM, or random access memory. Think of this as the CPU's workspace, or its short-term memory. It holds all the stuff the CPU needs to get to right now. But, and this is key, when you turn the power off, RAM forgets everything. And finally, you have I/O, or input-output. These are the computer's senses, the keyboard, the screen, the mouse, all the ways we talk to the brain and it talks back to us. Okay, so we've met the hardware team. Now it's time to meet the hero of our story, the protagonist of this entire journey, a single, humble computer instruction. This little guy is the absolute fundamental unit of everything that happens inside that box. So what is an instruction, really? Well, deep down, it's just a bunch of ones and zeros. But it's easier to think of it like a very simple sentence. It has a verb, which we call the opcode. That tells the computer what to do. Add, move, or store. And then it has a noun, the operand, which tells the computer what to do it to. So an instruction could be something as simple as add the number 5 to what's in memory location 10. Verb, noun. That's it. And this right here, this is the key. Every single app, every website, every game you play, it's just a program. And a program is just a huge, long list of these tiny, simple instructions all laid out in a very specific order. That's all software is, really. And now we get to the really cool part. We're going to follow our little instruction on its big journey through the CPU. This journey is called the instruction cycle, and it is the constant, rhythmic heartbeat of every single computer on the planet. This whole seemingly complex thing boils down to a super simple three-step dance that just repeats over and over and over. Fetch, decode, execute. The CPU fetches an instruction from memory. Then it decodes it to figure out what it's supposed to do. And finally, it executes the command. Fetch, decode, execute. Let's break that down. So, step 1, fetch. Inside the CPU, there's a thing called the program counter. Just think of it like a bookmark that's always pointing at the exact memory address of the very next instruction in line. The CPU takes that address, goes out to RAM, grabs the instruction waiting there, and brings it back inside to a temporary holding spot called the instruction register. Job done. Next up, decode. Now that instruction is sitting in the instruction register, and another part of the CPU, the control unit, comes over and takes a look. The control unit is basically the translator. It looks at the opcode, the verb part, and figures out, okay, what are we actually being told to do here? Is this an add, store? It deciphers the command. And finally, execute. The control unit sends out the signals, and the command actually happens.
If it's a math problem, the data gets sent over to the ALU, that calculator we talked about, and it crunches the numbers. If the command was to move some data, that data gets moved. The action is completed. And the second it's done, the program counter clicks over to the next instruction, and the whole cycle starts all over again.
So that's the basic theory, right? Fetch, decode, execute. But real CPUs have some seriously clever tricks to make this all happen even faster. Let's take a look at a legendary chip, the Intel 8086. It's basically the great-great-grandfather of the processor that's probably in your computer right now. The absolute genius of the 8086 was splitting the work into two specialized teams. You had the Bus Interface Unit, or BIU. Its only job was to fetch instructions from memory. It was the delivery guy. And then you had the Execution Unit, or EU, whose only job was to decode and execute those instructions. They work in parallel, at the same time, and that's the secret to its incredible speed.
And this technique is called pipelining. It is an absolute game changer. See, while the execution unit is busy working on one instruction, the bus interface unit isn't just sitting around. It's already out there fetching the next few instructions and lining them up in a little queue. This means the execution unit never has to wait. The moment it finishes one task, the next one is literally sitting there, ready to go. It's a perfect assembly line for instructions, and it makes everything ridiculously efficient.
We've been focused on the journey of just one tiny instruction, but now it's time to zoom all the way out and just appreciate the unbelievable, mind-boggling scale at which this simple cycle happens inside a modern computer.
You've heard of processor speed, right? Measured in gigahertz? Well, a gigahertz is a billion cycles per second. So a 3 gigahertz CPU is running that fetch, decode, execute loop we just learned about over 3 billion times every single second. That simple little three-step dance is happening at a speed that is it's almost impossible to really comprehend.
And that's the secret, really. The incredible power of a computer, it's not magic. It's not some mysterious artificial brain. It's just the relentless, perfect, high-speed execution of a very, very simple process. Fetch, decode, execute, over and over, billions of times a second. That simple little loop is the engine that powers our entire digital world.
Think about it. From adding two numbers together to rendering entire virtual worlds, it all comes back to that fundamental heartbeat. Which really just leaves one last question. If this simple loop built everything we have today, what's it going to build tomorrow? Thanks for joining me on this journey.